Okay, so let's start with the presentation about C++20, C++20 features. My name is Bartek, and if you don't know me, I'm author behind the C++ Stories blog. So let's get started. Here's the plan for the presentation. We'll try to talk about C++20 in general, and then I want to present 10 language features and then 10 library features, so that's in total 20. And then we'll have a look and some discussion about more features in the future for C++2023. That's already in the standardization process and almost ready. Okay, so if we go to this website, maybe I should reorder that. Okay, so if we go to that website, which is at cpp20reference.com, and if we count that, we have a list of, I think, all of the features that went into each C++ version. So like here we have C++20, 20 features. So those are core language features and then library features. And if we count them, we have like 80 library features and 70 language changes. And as you may know, C++20 is a huge change. It has huge changes. Like if we go, this is not sorted. I think this is sorted in maybe addition date or something, yeah, probably that way. Yeah, so if we have like, so with C++20 have features like concepts, right? So this is one of the biggest change. Then we have like this three-way comparison operator, so this is the spaceship operator. Then we have what have we here? Coroutines, right? So this is one. It even adds a new paradigm to programming in C++. Then we have modules, right? Another big change. And then I'm looking for ranges. There is this one range proposal. Oh, okay. Ranges are of course library features, so I'm looking in the wrong place. But if we go to library features, then we have like calendar and Timezone. Those are big changes for the library. Then we have concepts library, right? So this sort of addition of standard concepts. And then we have one range proposal, right? So introducing of ranges into the standard library. This is often called like standard library version 2 because it's so big. Yes, and then we have text formatting and various other things. So we have a lot of stuff, right? But in this so the question to you is also: have you tried C++20? Have you tried modules, format concepts, coroutines? You can answer it by yourself. But in this presentation, I want to focus on maybe smaller things that are sometimes omitted in various articles or quick articles that show only those big parts. And so let's have a look at those smaller parts. And the advantage of those smaller parts is that you can simply look them up, check how they work, and then gradually add to your code. So it's sometimes very easy to start using those new features. Okay, so now we can go to the first language feature. It's called abbreviated function templates and constraint auto. So this is quite complicated terminology, but it boils down to quite handy feature, quite handy syntax. And as you can see here, we have a pretty complicated function. It's called myTemplateFunc, and it takes parameter by using this auto keyword, right? So this is called unconstrained auto parameter, because there is no constraint here, right? So it's sort of like a T parameter from if you are using this regular template notation, and here we can also extend that and use concepts. So here I define a concept, signed integral, which is composed of two sort of predicates and two other concepts. So it has to be signed and integral, and we can create two functions, signed int only, and which takes this auto parameter, right? But it has a constraint. It's constrained by some concept, and here another way, float only function that takes parameters or arguments that are floating points. So it's a template parameter, but it's constrained with floating point. So this is like the shorthand notation. We can expand that into this signature. So we have this like regular template function with T parameter, which is signed integral. As you can see, this is not type name. There is no type name or class here. Or this float only function expands into floating point. So this is another shorthand notation for concepts. And this if we expand that into full version, this is a template with type name parameter, and then we can sort of translate that constraint here into requires expression. So that's another way of looking at that. In other way, we can say that you might know auto, so generic lambdas that take auto parameter, right? And it's expanded automatically by the compiler into a template parameter. So we can say that cpp20 got that generic syntax from lambdas from C++14, and it expanded into all functions, and now we can use that also with combination of templates, not templates but concepts. The key thing here is that you need to use this this constraint before auto, right? So it's not auto signed integral value, but it's the concept name and then the auto and the name of the parameter. If we stay with this with templates, as I introduced this concept of generic lambda from C++, from C++14, as you might know, this thing, so we have this lambda foo double, right, that takes two generic parameters. It expands into something like that, so it's operator, it's function operator, right, function call operator that expands into two different template parameters, so t and u usually, let's say, and it has some magic name, right, that is compiler generated. But the problem with this syntax was that inside this lambda body you could only use to get the type of this x and y, you had to use like decal type or something like that to get that. So like C++20 or the other way around, generic lambdas affected C++20 and extended that to regular functions, but also templates also affected lambdas. So we have this bidirectional sort of influence here. And in C++20 we can write code like that. We have this lambda or template head, something like that, that we can add to lambda syntax. So it comes after this lambda introducer. So we have the introducer and then the type name, and then the regular like template syntax, right? So there is no template, but this is sort of implicit here. And then we can specify vector of t elements rather than just having auto vector or something. And here we can pass that to use regular functions. Also, it's possible to use to add constraints into generic lambdas. So like here we have this signed integral that I added to generic lambda. So that's also this influence, so bidirectional influence that we have. Okay, so if we go to another topic of const expressions, we have a lot of so as you may know, const expression functionality got into C++11 and it was quite limited at that time. And with each revision of C++, we sort of lifted those limitations. And in C++20, you can even have unions, so try and catch work also, sort of work. Dynamic cast, we have also const expr allocations, we have even virtual calls and various library bits, but we will talk about that later. So you might ask about this try and catch. So the key thing here about try and catch is that before C++20 you couldn't even write try and catch bits in that in your functions. But right now in C++20 you can write that, but the compiler can only execute this try sort of path, right? So if there is an exception, if there would be an exception thrown during the execution, you get into catch statement, and this is not possible in compile time context, right? So you will get an compiler error if your code tries to attempt this catch path. So that's even handy for checking your code at compile time. So that's quite interesting. Then we have this dynamic casts and another part, context per allocation. I have even blog post on that. You can check on CPP stories. And here the compiler can allocate some memory, right? So you can use this new expression, but the core part here is that this memory block that you get cannot outlive the computation of this compile time computation. In other words, you cannot create a memory block and then sort of pass it to the runtime. So it has to be deallocated before. So it has to be deallocated after computation. So it's a step forward. Maybe we will have this limitation lifted, probably not in C++23, or I'm not aware of that. Yeah, but at least it is step forward. And then we have virtual calls, and all of that was actually needed, and a few others was actually needed to create context per string and vector into the standard library, and now you can use that in your functions. So we will talk about that later, but it's quite interesting technique. Then we have, let's go from those heavy features into something smaller. And we have a handy feature like using enum. Here you can use here you can see a source code with enum, which has let's say this is a long enum name, and before C++20, here is this path below. In this else case, you had to specify the whole name, right, of this long enum. So like long enum name and double colon and hello. But with C++20, and here you can also check that by using this feature testing that we also have, you can introduce this enum name as a prefix, and then the compiler in this context, in this scope, will help you with and make code shorter. So that's handy features. So you can basically introduce that name into like this namespace name into each scope. So that's okay. We are at point 5, and right now we also move back to templates, and this time we have a feature called NTTP, which stands for non-type template parameters. And before C++20, we could use non-type template parameter that were L-value references, integral types, right? So you could specify like size of an array, for example, a pointer type, a pointer to member, or enumeration. but in C++20 it's extended, and you can now specify structures and simple classes. It's called structural types, floating points, or even lambdas. This I'm not template expert, but this thing allows to create some magic compile time meta programming, meta programs. So that's quite interesting. I came up with this simple example, where, as you can see in Compiler Explorer, we have a class that's let's say gathers all constants, right? So we have like double gravity, and we have a function, member function that returns that gravity acceleration. And what we can do here is that we have this template function that takes a class which is a non-type template parameter, and then returns a weight using that gravity acceleration. So we have in this demo we have this two objects, constexpr objects, and you can specify, you can sort of pass that as a template parameter to this function, right? So I have this Earth gravity and Moon gravity, and I pass this weight like in kilograms, and I get weight in what's that? It's in newtons, I guess, right? And so you weight six times less on the Moon than on the Earth. So that's very handy, and you can create, as I mentioned, probably some magic things using that extension. So it also handles floating point. So that's also lambdas, but I'm not sure how to use that. Maybe there are some more cases like that. Okay, let's have a look at another feature. This time we have a new keyword. So we might say that this is somehow a big feature. This time let's go to an example. It's very basic, but the key thing here is that we have, if we look at the top, we have X and Y. They are at global scope, so please use quite rarely and don't use it too much. X is 0 initialized, so this is not undefined or unspecified, but it has 0. And then we have Y, which is constant initialized, right? Because it's constant. 10 is a constant expression, so the compiler can use constant initialization to do that. And with const init from C++20, we can basically tell the compiler to force this constant initialization. Constant initialization is better, right, than the next step for globals, which is dynamic initialization. So, for example, here I have a global, another global, let's say global 2, which will be dynamically initialized. So during the program startup, if you may know, the compiler builds a list of functions, of initialization functions that has to be invoked to compute a value, and then this value is assigned. But it's better to do that not on runtime, but at compile time. And also with const init, not only we can force that, but also make sure that the initialization is safer. If you know this static order initialization fiasco, that's the problem that we might have. And with constant initialization, we can basically avoid that. So this is not possible for all for all things. You have to have this constant expression, but even in the case of the string, we can potentially do that. So all of those like resources and I don't know, names or dictionaries that you use, they might be well suited for this new keyword. So that's quite interesting and allows to have safer code, and especially if you have lots of translation units, which is what we have in most projects, right? So that's quite good to understand, right, and take leverage on that. And now we have a feature which went from C basically. So it's called designated initializers, and it's suited for aggregates. So if you have like date struct with all public members, then you can use those names, right? So dot and the name of a member variable to assign, and then expression, right, and assign that. So in short, it's much easier to read than this regular version that we got used to, I think. So it's easier to see what values are assigned to members. So this is mostly to interop with C language and make use of that. So this, as I mentioned, they have to be applied for aggregate initializations, and then designators have to refer to non-static data members. So if you have like static something, then it's not going to work. Designators have to be in the same order as in this class declaration. So you cannot mix that as in C language, for example. You cannot mix regular initializations with designator, so you cannot specify 2050 and then month and then day, right? Because all of that has to be specified. And you cannot nest a designator, so you cannot specify if you have like two dots, right? So like date dot year dot something, right? You cannot do that. Okay. Then another thing, no discard. No discard from C++ 17 attribute is very got very popular, I think, because we can also say that, and a lot of experts say that this is a new default that should be automatically applied on functions. So basically, no discard should be implicit on functions. I wouldn't go that far, but in a lot of functions, especially those functions that are computing something and returning something, then no discard is very handy. So in this with this feature that got into C++20, no discard is extended and simply allows to specify a message, right? Why this function cannot be or shouldn't be discarded. What's more, in the standard library, this attribute is applied on some some functions like async, allocate, operator, new, empty. So so this is very useful attribute and might point to some nuances and errors in your code. Then we have another language feature which is range-based for loop with initializer, and in short, it allows you to put something before this range-based expression. In this case, we can specify some index, right? Some counter that we use to use in that in a loop body, right? Also, as one potential use case, it can be used to hold temporary objects, right? So, for example, here, if you have like this auto x and for some reason foo returns like a vector or something, then though this can point to undefined behavior, because when foo goes out of scope, those items won't be extended, so the lifetime of those objects won't be extended. So it's best to copy that temporary object into some variable and then iterate on that. And this is now fine with range-based, with this initializer, where you can simply store that. It's just a shorthand syntax, right? Because you can simply write that code before this loop, right, and have everything and have the same result. But it's shorthand notation, and why not use that? And then we have another new keyword, const eval, which is like extension to const expr functions. Basically, const expr function allows you to compute something at compile time, possibly at compile time, and also at runtime, right? So you can use that function in a regular context. But with const eval, it's sort of forced to use at compile time. So this is like a new mechanism that you can use. So for example, here I have a const expr auto c, which comes from the sum, right, which is executed at compile time, because I created this const eval function, and it's fine, right? It's evaluated at compile time. Then we have then we have this sum c, which is const expr, and this is evaluated at runtime, right? Because I have this variable that will work at regular runtime. But if I want to do the same with another variable like d, and my function const eval, I will get a compile time error. Yeah, so this is suited only for compile time computation, and also I cannot create const eval variables. So that's one limitation of that. Okay, so we finished language features, and now we can move to some library features. Okay, let's go to some library features. The first one, let's say easy one, we have a lot of math constants that we can use, and probably the most like popular is let's say this pi number, and those are in the form of template template variables. Template variables, but also so as you can see, this p, pi, and v, right? Underscore v. But then the library also exposes those inline objects, right? Inline context pair variables, which are predefined to be which are predefined to be double types. But you can also use floating point, so that's your choice. Then, as I mentioned, we have this more context pair in the library. Let's try this example where we have string splitting at compile time. This was not possible in C++17, but now I have let's say a simple function that returns number of words, right? So that's a context pair function that takes a string view, right? And then it builds a vector of strings, right? So it takes this string, input string, then it runs some basic algorithm also on vector. So it has this, it takes string view, delimiter, right? And then it walks through the string and checks whether there is a delimiter, and if there is, then it pushes and places back a new word, a new token, let's say, and then it returns the output. So during the evaluation of this function, the compiler has to allocate some extra memory, and this is what I mentioned before, that we have this context pair allocation. So we have allocation, and then at the end this memory block, temporary memory block, has to be released, so it cannot go outside of the computation, and then we can return the size of that, right? So the size can go into a regular variable, but not that memory block. So it's non-transient allocation. Yeah, but as you can see, this code is regular, looks like regular runtime code, right? So there is no template magic here, right? But previously, before C++17 or C++14, that would be quite hard, right? And you would have to use some template magic to do that. But right now, most of the stuff you would expect will work, right? So that's very, very impressive. And then we have handy string functions, also string view functions, that allows you to check whether something starts or ends with some prefix or a letter. So before that, you would have to use some boost string algorithms, and right now this is just part of the library. And also I think that we will get starts with and ends with on ranges, so like non-member functions, so algorithms, range algorithms. So you will be able to use that on any container, basically on any range. So that's very handy. Then we also have contains member function for associative containers. So before that, right, before contains, specifying contains, you would have to basically look up this key, right, and then check whether that's pointing to an end iterator or not. And right now you can just use this member function contain. So this is for associative containers. Then we have consistent container erasure. This is this erase remove idiom improvement that we got since early days of C++ standard library. So as you can see, as you may know, remove algorithm doesn't remove, and you have to use some erase functionality from this particular container that you are using. And in C++20 this is sort of combined and standardized, and you can use this erase non-member function that takes the whole container. So basically we have this lots of overloads for each container, because each container might have some different mechanism to invoke this erasure. But so we have this layer on top that allows us to use this non-member function with some predicate or not, depending on what you want, and it does what it says, right? So it erases some elements from the container. So it's very easy to use and much better than this erase remove idiom that we had. Now we have this source location, which is another step forward into removing macros from your code. So rather than specifying this hash line, hash file, we have an object that is named like that has a name source location, and you can initialize that with source location current, and it will point you to this location from the point of invocation. So of course it's best to see an example. Okay, so where should we start? I think this one. So if you have a log function, it calls with hello world, so it points to this function. Okay, so we have this message, and we have this source location initialized with current. And as you can see, we'll have this. So we say we then output that with this info message, name, line, and function name. And as you can see, we have info, file, line, and function name, right? So it was initialized inside this main function at line 31, right? So that's correct. We can also specify another log, right? So it's also correct, and we can use that to have this trace location example that uses this variadic arguments, where we can specify more data, more arguments with string stream, so string stream. And as you can see, the one limitation is that this source location has to go at the front of the whole list, because we don't have this what's the name for that, non-terminal variadic argument. But there is a trick for that, so if you want, you can see this my blog post on that. So basically we can use this somehow. We can use this additional object to hold this source location for us. Okay, let's continue. Now we have this bind front for partial function application, and in short, this is an improvement over stud bind, right, that we have, I think from C++11. In many articles, stud bind is considered unsafe, and there are some tricks with that, or catches, but so you can have a look at this article from Upsale blog, but it's also not that handy to use, because for example, if you have like a function taking 4 arguments, and you want to fix those first 2 arguments, then you have to use those placeholder syntax, right, to generate that function object. On the other hand, with bind front, you can just take the function and then specify what you want to fix, counting from the start, and then call it like that. If we run that, then you will get the same output, of course, but it's much easier to read and use. So that's one advantage. Okay, so let's have a look at another feature. This is called heterogeneous lookup for unordered containers. So it's best to to work on an example, quite long example, but okay, it's running. So what we have here, so if we have things like dictionaries, and those okay, so let's start from the top. If we have a regular like dictionary, so string to integer mapping, and then we want to okay, so we initialize that with those long strings, and then we perform this lookup. Then we have to and we perform this lookup using a string literal, so it's not the type that we store in our dictionary. So currently each container will have to that function will have to convert that into the key type, and then perform the lookup. So for example, if we have this lookup in normal, then we have another allocation, so allocating 24 bytes, and then we can specify whether we found that or not. So we found that. But on the other hand, if we have this transparent map, so it's specified as unordered map, string and int. We have this string hash function and equal to transparent operator. So this is a bit more complicated than with ordered maps and sets, because this time we want to provide support for hashing functions, for hash functions. So it has to be so we have to provide this equal to transparent operator, which allows to compare keys of the different types, but matching types. So like string with string literal or string view, but we have to provide support for hashing. So that's the one extra step that we have to invoke here. And as you can see, we perform the lookup by const char, and there is no extra memory allocation going on, right? Because we have this string already, right? So there is no need to copy that. While with normal maps, we have to perform this extra step. The same happens for const char and string view. There is no need to allocate anything. So this is not enabled by default, because you have to sort of implement that on your own, but it might be might give you a speed up in some critical code paths that you might have. Okay, we are almost near the end. Then we have this short function, so short feature, but on the other hand with long name. So basically, if you since C++11, let's say we should be using we should be using smart pointers, right? But there are some differences, and for example, by so from the start, make unique uses this form of memory block allocation rather than this one. And the difference here is that this one invokes a default constructor, right? So for each element of, so for each int in this case, you will get a you will get a default constructor called. In this case, it will initialize int with value of 0. But with this case, we only allocate memory for this type, but there is no need to. But there is no invocation of a default constructor. While of course it's best to specify the value and initialize a value and variable with some value, like with zeros or something. Then for performance critical code, this might not be what we want, because for example, you might, so usually for example, if you read some data from a file, you allocate a memory block and then you immediately read bytes from that file, let's say. So you are handling that initialization step correctly, but you simply have two steps. So in order to save time, you can use those new functions in order to save time and also still be able to use smart pointers. You have new functions, new make functions that have this suffix for override. And if we go to Compiler Explorer, I have this benchmark, and if we wait a bit, we can see that allocating like 10,000 integers takes 10 milliseconds, but on the other hand, using that new function for override, it only takes less than a millisecond, so it's like 100 times faster. Similarly, for make shared, we have 62 milliseconds, but it's just a fraction of millisecond for override. So as you can see, even setting elements to 0 might have some cost, right? So it's C++, and we want to have a choice. So if you really want to make those numbers smaller, then you can use those new functions. Of course, we have to take that into perspective. And for example, if we have a function that takes right, so it creates that memory block and then loads that with some data immediately, then you will not see this 100 speed up, right? Because that's normal memory copying or memory transfers. So for example, if we have like this more realistic scenario, then we don't have 100 times speed up, but we have this only slight speed up, right? For this case. So that's the that's one thing to mention. Okay, and then if we have, okay, and the last one about safe integral comparisons and S size. Initially I was surprised to see them. I didn't know what they mean actually, but then I started looking and I even wrote a blog post on that. And basically we have a situation where when we mix numerical types, we might get different results and sometimes unexpected. So the problem here is that long compared with unsigned short gives true, so minus 100 is smaller than 100, but when you compare that with a number like of type size t, which is unsigned long, for example, on many systems, on many 64-bit systems, and then you will get a false, right? Because long will be converted to unsigned, so it will become a super large number. And as you can see, similar code might give strange results because of numerical integral conversions. And with those safe functions, the signedness will so it will compare with this mathematical node modulo to arithmetic, and it will be easier to predict what should happen. So basically, if you have different signedness, then they will have to be converted. So like if you have this long number, then so negative, and then size t, then the size t will be converted to signed number, and then compared, so that it will be in mathematical sense not modulo to arithmetic. And then we have this S size function which takes which returns signed integer, and this signed size for containers. In many cases, I've also heard that having unsigned type for sizes is also not maybe not appropriate, but is not the best default that we get in C++. And because it's easy to mix signed and unsigned types, which might be problematic and generate unsafe code. But right now you can use this S size function, this non-member function, which returns signed size. So for example, in this case, before C++20, if I have this size which is unsigned, I could get an error and runtime error, infinite loop, because size -1 for empty vectors would give me -1, then converted to unsigned, which would be very large number, and then I would get into access violation, probably, hopefully. But with S sign, then this is expected there, right? So I will get 0 -1, which is -1. So that's sort of for for using the correct sort of arithmetic. If you want to stay in this modulo 2 arithmetic and you know what you are doing, then it's fine, right? You can open the hood and use that. But if you are unsure or want to have this safe mathematical reasoning, then just use those functions and should be safe. Okay, and so that's definitely not all that from C++20, and you can explore, as I mentioned, that huge list of other features. You can also have a look at this great book by Nikolai Yosutis about C++20. There is also a recent presentation from Google Chrome about how to use C++, maybe not how to use, but how they used and applied C++20 in their code, and what limitations they got, and what issues they found, and how to overcome them. And you have also like 60 plus articles about C++20 features on my blog, so I invite you to that. And in summary, we have this. I would like to say that we have C++20, which is a huge addition with large features, modules, coroutine ranges, concepts, but we have lots of small stuff.